All right, so for 6 application problems, we're going to look at how you can apply logs and exponentials to solve an application problem. So here, we want to suppose that you invested $1,500 at an annual interest rate of 8.5%, and they want to use this formula to determine how long it will take to double your investment. So plugging in, we have this formula right here, A equals PERT. Your initial investment is going to go ahead and go in for P. We have E to the R, so I have to switch this 8.5% to a decimal. So it's going to be 0.085. And then we are trying to solve for T. If I'm going to double the investment, we're going to go from $1,500 to $3,000. So there's our setup right there. And then from here, we're trying to solve for T. So just like we did in the other problems for 6, you got to get the power by itself. So you're going to divide each side by 1,500. It's going to give me 2 equaling e to the 0.085 times t. At this point, there's nothing outside the power, so we're going to go ahead and switch forms. Switching forms, it's going to turn into the natural log of 2 equaling 0.085t. And then it's all calculator driven. So we're going to take the natural log of t, so ln t. And then after we get that answer, we are going to divide by 0.085. And it's going to give me t to equal 8.15 years. For number 2, they give us radioactive substance, and it talks about how much is remaining after a given amount of time, in this case t years. So for A, they want to know how much of a 40-gram sample will remain after 25 years. So we have an initial amount of 40. We have e to the negative 0.0277, and we are multiplying by 25. So this one, there's no magic to it. Like, there's very little math you have to do. We're just plugging in the calculator. So we have e. Sorry, we should have a 40 out front. So 40 e to the negative 0.0277 times 25. And after 25 years, we're going to be left with about 20.01 grams. For B, they want to know how many years will it take until only 10 grams of the 40-gram sample remains. So this is one where we're going to have to use logs. We're going to have 10 equals 40. We have e to the negative 0.0277, and then we need to solve for t. So just like we did on the last one, you're going to divide each side by 40. I'm left with 1/4 equaling e to the negative 0.0277t. At this point, the power is by itself, so we're going to switch forms and have ln of 1/4 equaling negative 0.0277t. And then in our calculator, we're going to go ahead and do ln 1 divided by 4. And then I'm going to divide by negative 0.0277. So divide negative 0.0277. It's going to give me an answer of about 50.05 years. Okay. And then our last application problem, number 3, we're going to follow, sorry, there's 2 more. You're going to follow the same stuff, right? You're just plugging in. So you read the problem. They say the moment of magnitude m of an earthquake. And then we want to solve for E, energy. So I go ahead, plug in. You got 9.5 equals 0.0291, natural log of E plus 1.17. On this one, to get the log by itself, you go ahead and take 1.17 away from each side to give you 8.33 equaling 0.0291 ln E. You have to divide the 0.0291 over. And then for this one, since the log is by itself, we switch forms. When you have ln, the base is e, so this turns into e to the 286.25. It's going to equal our energy. So E to the 286.25. And it's going to give us an overflow error, so I'm actually just going to leave it like that. For example 4, you're going to follow the same rules. You're going to go ahead, plug in, and then we're going to switch forms to solve. So that's 6-6 application problem.